So welcome back to the video on lecture number 10. And first of all, let me apologize for being slightly late in uploading the video. However, you were given an assignment and which required you to go over all the slides and apply everything that was taught during the lecture. So I think by the time you view this video, you would have gained all that is necessary out of these slides. And therefore, use this video just as a reminder. And hence, I won't be going that deep. I'll just touch the basic things that you ought to remember. Okay, so let's move forward. As always, uh, the learning resources with respect to software is the works online documentation. However, when it comes to thermal systems, we'll be needing a lot of data sheets to figure out or to find out what certain properties of physical solids, liquids, and gases are. Since we will be dealing a lot with such properties when it comes to thermal systems, and therefore I have provided a few data sheets, few online data sheets, mostly coming from a website called engineeringtoolbox.com. And this website is what I have used since my undergrad days and in the industry to some extent as well. So I'm quite confident and about the credibility of the data in this website. And since it's used a lot in other engineering related YouTube channels as well, this is kind of a website that you can refer to without any doubts as to the credibility. Right. So that being said, let's just move on to touch up on the theory. Okay, so we are studying thermal systems, and let me give you a short and concise description of what a thermal system really is. And that I've been doing that with what I have stated here in the green letters. A thermal system is which transmits energy from a source to a sink through conduits, with some being stored in accumulators. Right? So that's a single sentence explanation of what a thermal system is, and quite an abstract one at that. Right. Now I want you to focus your attention on the keywords in our explanation. The first is energy, the second being source, third sink, fourth conduits, and finally we have the accumulators. So let's go through these keywords one by one. Now, the first one is energy, and we are talking about a specific kind of energy, then that's thermal energy. Now, thermal energy, in essence, is about the vibrational energy at an atomic level for any given solid, liquid, or gas. Uh, I'm not talking about the visible vibration that you see in an object, but the vibration at an atomic level. So it's invisible, and how humans and other objects perceive thermal energy is through the metric called temperature. You all know what temperature is. We feel thermal energy through temperature, and we measure thermal energy by measuring the temperature of an object, whether it be solid, liquid, or gas. Right. Now, let me leave what sources and sinks are to be discussed later, and let's move on to discuss what accumulators are. Now, accumulators, by the definition of the word, are objects which store thermal energy. Right? Now, as per the definition of the Kelvin temperature scale, any object which has a temperature higher than the absolute zero will have some energy stored within it. In a practical case, every single object that you encounter in the world will have a temperature greater than 0 Kelvin, and therefore every single object, regardless of the phase that it is in, is an energy accumulator of some sorts. A metric of how much energy has been stored is once again the temperature. And if some object has a higher temperature, then that means that object has uh, an atomic level has a higher energy stored within it, within a given within a unit mass scale. And if an object gains energy, that object will gain atomic level vibration. That vibrations will be stronger, and that will be indicated by a higher temperature. So if an object has gained temperature, that means it has stored some energy, uh, thermal energy. In a similar manner, the same can happen in the reverse. If an object loses temperature, it will have to lose thermal energy, and that means it has lost vibrational energy at an atomic level, right? So that's what accumulators are and what accumulation is. So the indicator of how much energy is stored uh, is, of course, once again the temperature. Okay, then let's move on to the keyword conduits. Conduits, by the definition of a word, is a pathway for anything to be transferred. And in this case, the thing is energy, and for the transfer of energy, there are only three such conduits: conduction, convection, and radiation. So I guess you know what these things are, having studied thermodynamics at an earlier level. But let's just briefly discuss what they are. So conduction is the transfer of thermal energy to neighboring atoms, I would say, uh, in the an absence of bulk particle motion is prevalent in conduction. Once again, thermal energy is transferred to the neighboring particles in lieu of bulk particle motion. Why I brought in bulk particle motion is that it would be a key factor in differentiating between conduction and convection. Since in convection, the transfer of energy is predominantly due to bulk particle motion. And by bulk particle motion, I mean particles moving around. A concrete example for this would be, so the concrete example would be a heated plate and the transfer of energy from that heated plate to the ambient environment. So we were discussing, yes, we're discussing convection. And I was trying to give you a concrete example to differentiate between conduction and convection. Okay, so we have a plate which is being heated through some means, let's say through a resistor which is being powered, not a resistor but some kind of heating coil which is being powered using electricity, and this is the plate which is being heated. Energy, thermal energy will transfer. No, oh, sorry. Let me begin. The source this time would be the electrical energy. It's converted to thermal energy at the heating coil, and that converted thermal energy will be transferred uh, into the rest of the heated plate through conduction. So the particles nearest to the heater coil would gain energy, and afterwards, the next set of particles closest to the previously heated particles would get transferred a bit of energy, and so on and so forth. The energy will be transferred from one neighbor to another until there's a yeah, until certain conditions are met. Discussion of that conditions would be quite out of topic, but what you need to know is how energy was converted from electricity to thermal form and transferred through conduction throughout the heated plate. And notice the lack of particle motion. The energy was transferred, the particles didn't move. Now, once the heated plate is heated to a temperature, theoretically, a slight increase beyond the ambient temperature is fine as well. But let's say we heated it beyond to a certain amount. So that was conduction. Now, once the is heated beyond a certain, at least theoretically beyond the ambient temperature, energy will start to transfer from the plate to the ambient atmosphere. Let's call it that. So surrounding the plate will be gas particles, and let's see how the energy transfer occurs. First, there will be a surrounding layer of gas in the extreme vicinity of the plate, and through that gas layer, energy will once again be transferred through conduction. It means energy will be transferred to the neighboring atom, and after that, due to the gain of energy, and the temperature will rise. And if you remember your gas laws, gases with higher temperature will have lesser density, and when a portion of gas has lesser density than its surroundings, it will float. It means a gas over here would expand to a higher volume, and it would the density would be less, and it would float upwards. And what was initially at the top would move downwards, and upon moving downwards, they would gain heat from the plate. They too would also expand, and they would move upwards. And this motion would keep happening in a cyclic manner, and the energy will with some time be transferred from the plate to the surrounding atmosphere, and that energy transfer happened due to the bulk motion of these gas particles. And that's the differentiation factor between conduction and convection. And if I were to further simplify it, conduction is predominant in solids and convection is predominant in fluids, that means liquids and gases. Convection does not happen in solids, since in solid, within the solid, the particles, there's no bulk motion of particles, right? So that's some physics for you, just as a reminder. Mm, but this is not a physics module, but if you are going to model physics, then we should at least know what physics are first. Okay, so let's discuss radiation. Now, I hope you have studied this, but I think you have on the thermodynamics in a previous level, that any body with a temperature will be emitting electromagnetic radiation. So anybody with a non-zero temperature would be emitting electromagnetic radiation, and that it's not really visible unless that electromagnetic radiation it's emitting is in the visual range. And an example for that would be the filament of a light bulb, and the particular certain portion of energy emitted or radiation emitted from that filament would be in the visual range, and therefore you would see it. However, every single body, every single solid, liquid, and gas in our surroundings is emitting radiation all the time, because every single solid, liquid, and gas has a non-zero temperature. Therefore, it's emitting radiation, but it's not visible since emitted radiation will usually not be in the visual range unless in certain cases, such as the filament, where they are heated to extremely high temperatures. Right. So every single body emits radiation, and at the same time, they absorb radiation from the surroundings as well. So keep this in mind when we move on to modeling thermal systems. I think I just described what the three conduits are. So let's move on to discuss what the sources and sinks are. Now, if you remember the zeroth law of thermodynamics, I don't know whether it's the first or the zeroth, but however, there's a thermodynamics law which states that energy cannot be destroyed. I think this is the first. Energy cannot be destroyed, nor created. It's only transformed from one form to another. But that means, uh, even though that we'll model some source, will have some source and sink in a computational model of a thermal system, in reality they aren't really sources and sinks. But however, in reality what we see is conversion from one form to another. And in our thermal systems models, when a conversion happens which converts some form of energy into thermal energy, we call that a source. And if there are some conversions going on which convert thermal energy into other forms of energy, we call them sinks. Right? And apart from that, our thermal systems will have boundaries, and whenever energy enters that boundary or enters that boundary to a conduit, we'll call them sources. And whenever energy exceeds that boundary, we'll call them sinks as well. Right? So there will be two cases of sources. One will be where energy converts into thermal energy, and another where thermal energy enters our boundary. Uh, those two cases will be called and modeled as sources. And whenever energy exceeds our boundary through some conduit, we'll call them a sink. And whenever energy is converted from thermal to another form of energy, we'll call them as a sink as well. Right? So that's kind of an abstract description of what thermal systems are and how thermal systems are modeled. I think it would be more clearer too as we move on to the demonstration, and I'll show you a real case. So moving on to slide number 4 from 3, I have given you 4 equations and I've left a certain portion kind of empty. So let's discuss what these equations are. So we have 3 equations which describe the energy transfer through conduits. They basically relate the rate of energy transfer through that conduit, which is Q, to certain physical properties of that conduit, which are characterized by H, K, E, Z, so on. Geometric properties of those conduits, which are characterized by the surface and cross sectional areas. And we'll get Q2 temperature differences and temperature gradients based on the type of conduit. Right, so these equations are quite straightforward. I have given you the equations and I have given you the definitions of the terms. And when we move on to the complete demonstration, it should be more visible to you, or more clearer to you. And then we have an equation which relates the quantity of energy stored to two physical properties of an object. And by object, I mean liquid, gas, or solid. And to the temperature gain or temperature loss within that object. And finally, we'll need to figure out how to model energy sources and sinks. Now, there's really no definite hard and fast equation that I can offer you to model energy sources and sinks. So we have to take energy sources and sinks, look at the problem definition, and figure out how to do it. So it needs to be considered on a case by case basis. And if you really want to master this thermal systems modeling, then you will have to take a look at multiple such cases, perhaps in textbooks, and you'll need to kind of master how to model energy sources and sinks for different types of cases. We'll be studying one such case today, and I'll show you how to model the energy source and the sink for that case. Right. So now you have all the necessary tools required to mathematically model a simple thermal system, and yeah, and that I would kind of say that there's another limitation, and that would be you would be limited to 1D dynamic dynamic thermal systems as well if you're going to use these set of equations, since these are the simplest. These are not uh, these are actually a extremely simplified version of some advanced generic equations for energy transfer. And due to us using this set of extremely simplified equations, we'll have to work under that 1D dynamic system limitation, right? So that would be the scope of our mm, lecture and module. Just know that we brought that limitation upon us due to using this set of simplified equations. If you want to break away from that limitation, you would have to look up more uh, the more generic case of these equations and move into that higher dimensionality, right? That would be kind of out of our scope. Right now, since the best means for anyone to learn mm, concepts is to apply them to solve some problem, we'll be discussing such a sample problem. So we'll be looking at an extremely simplified thermal system of a heated orb, and I have given the problem statement over here. Under the problem statement, I have specified some geometric properties of an orb or a sphere, which I would like to call it. I have specified the material that the orb is built out of, which you will see that you'll need in order to figure out the density of the material and thermal emissivity. Yes, and what else? Yes, thermal conductivity of that material as well. Of that object as well, you need to know what the material is. And then I have specified how it's being heated and at which rate. I have specified that rate as x uh, in order to maintain generality. And then as the objective, I have requested you to obtain an expression for the variation of temperature of the orb with time. That's our statement. And I have given an assumption which asks you to consider the orb to be highly thermal conductive, extremely thermal conductive, and this is quite contradictory to providing you material of the orb. But however, unless we make that assumption, we won't be able to use the equations we just learned now, and we won't be able to use a software like Simscape. We'd have to venture into other. We'll have to venture in the domain of partial differential equations and use FEA software like ANSYS, SolidWorks simulation, or SimScale, right? So this it's a good thing to know that we are able to use this assumption in order to reduce the dimensionality of the problem and to tackle it with our mechatronic system modeling software, which is SimScape, right? So that's why I brought in this assumption. But this assumption would make you believe that the orb is higher, almost infinitely thermally conductive. But if it's built out of aluminium, then it cannot be. It would have finite thermal conductivity. Uh, we'll just disregard that for now. So this assumption will be used to ensure or to assume that there's no yeah, it will be used to kind of bypass study of the three-dimensional thermal conduction within the orb. If I use this assumption of the orb being an extremely high thermal conductive material, then the uh, resultant of that would be the temperature would be uniform throughout the orb, thus eliminating the need to modify the tridimensional temperature distribution. Right? Thereby, we reduce the dimensionality of the problem that we are going to solve. Mathematically put, uh, this would just enable us to assign some variable as the temperature of the orb, and this temperature would be the temperature throughout the whole and at the whole of the orb and at the surface of the orb, right? And finally, I have given you a fact: the ambient temperature is 30 Celsius, and we would be needing this fact in order to figure out the rate of heat transfer from the orb to the atmosphere. Okay, so that's the problem, and let's see how we tackle it. So, as with any such system, when we come to modeling, we first decompose it down to the core components of that system. So now we'll go back to our explanation of what a thermal system is. Energy will transmit from sources to sinks through conduits, with some being stored in accumulators. Now the source is given in our problem statement. It's a conversion of electrical energy into thermal energy. That's what a electric heater does. And our sink would be atmosphere. It's not explicitly stated, but you should be able to figure it out since that's once the so we will be studying energy transfer from the heater to the orb and from the orb to the atmosphere, and once it's reached the atmosphere, then there would be nothing. I haven't exactly stated whether there's anything downstream which would be absorbing that energy, and due to me not mentioning such and subsequent element, would have to conclude that our sink is the atmosphere, right? And finally, we have some transfer routes. We'll discuss them in the next slide. And so these are the core components for a thermal system. In addition, we'll have an energy accumulator as well. But once again, due to me using, yeah, of course, there will be an accumulator, and that would be the OP, although I haven't specified it. However, we'll see it in the next slide. And finally, since we are dealing with mathematics, and for us to obtain an expression for the temperature variation, we'll be introducing a variable called surface temperature of the orb. And even you can disregard the surface thing. Even if you take the variable as just the temperature of the orb, that would be fine, since due to this assumption, the temperature would be same throughout the entirety of the orb and surface as well. Right. So let's move on. Let's kind of draw thermal energy transfer routes. So what you see as the circle is a 2D representation of our orb. You see my electric heater. It's converting the electricity to thermal energy. Then that energy is being lost through radiation to the atmosphere and being lost through convection to the atmosphere. And at the same time, if you can remember what we discussed on radiation, any object can absorb radiation as well, in addition to emitting it. So that's what I have represented over here. So now this is not an extremely formal method of mm, denoting energy transfer, and for that we'll be using block diagrams like this. There's no difference between those two. It's just that this is what you'd see in most textbooks, and this is invariant. So this notation is invariant of what type of thermal system you're modeling. But- So those things are basically the same, and used just used for us to gain a knowledge of, or just for us to note down how energy transfer happens as an assisting tool for about to come. Right. So we have three conduits of energy transfer and one energy accumulator, which is the orb. So we'll write down the equation that I have already given to you for each and every one of these conduits, and for the accumulation, we will replace the terms as necessary. Mm, So if we take convection loss, we have H, which would be the coefficient of heat transfer from the orb's surface to the atmosphere, and the surface area of the orb, and finally the temperature difference between the surface of the orb and the ambient. These things will be so these two terms will be quite straightforward. But as for the heat transfer coefficient, that needs to be found using a data sheet. So we'll go to the website that I recommended, Engineering Toolbox, and you will come to a particular chart or a plot which gives you the heat transfer coefficients at certain air velocities. Now, what you can infer from seeing a graph like this is that heat transfer coefficient would be dependent on the air velocity. That means the heat transfer coefficient increases if there's a high wind around. And I haven't explicitly stated what the air velocity is in the problem statement. So therefore let me assume that the air velocity is at its least and take 25 as the heat transfer coefficient. That's something you can do if I haven't explicitly stated the air velocity. But if I do specify it, Then you'll have to figure out the corresponding heat transfer coefficient for that air velocity. So we'll take 25 and move on. Now this H can actually be evaluated theoretically, but we'll have to do some complex mathematics for that, and that's beyond our scope. For our purposes, using that experimental data and figuring out it should be totally fine. Now, on another note, knowing when to use the data sheets and when to use complex mathematics is another skill that you need to master if you are moving into advanced systems modeling. Right? So, based on the accuracy that you want for your results and based on the safety factors or how safe your final system needs to be and how critical your final system would be, you need to make that decision. But that's up to you. For this module, we'll be using the datasheets. Right? That's an important thing to know. Okay, then let's move on to the radiation loss. The equation is given in the previous, the generic equation is given in a previous slide. Uh, so I think these two terms are straightforward. Z is actually the Stefan Boltzmann constant. It's as the name implies a constant. And for emissivity, we'll have to use another assumption that is the emissivity of the orb surface is 1 for all frequencies. Right. So once again, this emissivity, in the real case, the emissivity depends on the nature of the surface and the nature of the coating that's applied on the surface. And it's kind of like H, where you can either model everything down to the last detail and evaluate an actual emissivity, or you can do some experimentation and figure out what the average emissivity is, or you could roll with an assumption like the one I had given over here. Right. So for clarity, I'm using emissivity for both absorption and emission throughout the entirety of the frequency spectrum. So you just have to plug in E equals 1 over here. The same thing goes for absorption of radiation from the surroundings. And finally, the rate of heat transfer is x, as I had given to you in the problem definition. And for the heat accumulation, the thermal capacity can be found out. The specific thermal capacity of the orb can be found out by referring to the once again to a data sheet, and the mass can be found out by evaluating the volume and multiplying it with the density. Specific heat, and once again in another tab you'll be able to find the densities as well. Okay, so in that manner you'll be able to write down this expression for each and every one of these conduits, sources, and finally the accumulation. And I think I gave a demonstration to you during the class about how to use Wolfram Alpha and to quickly gain so mass of This is one such free tool that you'd be able to use not during the exam, but throughout the later portions of your life to speed things up instead of going to each and every one of these data sheets and looking up masses, evaluating the volume, multiplying them together, and losing a bit of valuable time. Instead of doing that, you can use tools like this to do the heavy lifting for you and let you focus on what's important, which is developing the model itself. Right. Okay. Now, so once we have developed these individual expressions, we'll use the first law of thermodynamics, which means there's no net creation or destruction of energy. And we'll express this in mathematical form. Sorry. And we'll replace each and every one of these terms, which the terms that we have developed. And upon expanding them, simplifying them, and rearranging them, we finally come up with an equation like this, which is an ordinary differential equation of first order, which can be solved using MATLAB, and this can also be implemented using Simulink and solved. And I think that's the first portion of your assignment. But however, the second portion of this particular lecture will be about bypassing this whole quite cumbersome steps of developing the model and instead using Simscape to model things as we see and eliminate perhaps human errors, which definitely arise during lengthy and cumbersome tasks of developing that ODE. Right. So let's move on to Simscape. So from the domains that we have already studied, electrical, mechanical, batteries, yeah, perhaps those are the only cases that we studied in Simscape. So what you must have gained out of those demonstrations of Simscape is that what we build in Simscape or what we implement in Simscape would be kind of a diagramming method of what is actually going on. It would be closer to what we draw instead of being something a mathematical expression like this. So if you can use your intuition to develop a diagram like this using Simscape, all you have to do is implement that one, and you will have need to have a knowledge, and you will need to have a knowledge of what the blocks are and which blocks represent which of these things. And once you know that, it's just a matter of implementing the diagram as you previously drew it. And perhaps there will be some conventions you have to follow, like this thermal reference. Right. Now, so this is what I've developed. And the first difference that you'll notice is the set of scopes and networks I have on the right. The previous demonstrations I didn't have this, and I simply connected a bunch of blocks here and there and a bunch of display blocks as well. So that would make us lose clarity in our physical model. So what I have done is I have used a block called go-to block and use another block called from block in order to keep the blocks away from our physical model. Right. So I have kind of kept those things apart. But the connection exists. Choose what from go to and a from block means is that behind the curtains there's a connection between each of these blocks, similarly named from and photo block. It's just a tool provided to us by Simulink, which you can use to make things clear. Now, uh, so since you have, by the time that I'm recording this video, you all have submitted this assignment. I have gone through your submissions as well. Your assignment has been done properly. And since we already discussed this in class, you know what this is. But just let me go through a few of the things which are unique to the temperature domain. So, thermal reference is the 0 Kelvin point. Nodes on a network are kind of like interfaces between objects. True variable is rate of heat transfer, and the across variable is temperature difference across two nodes. So our thermal system will have a source, a sink, and energy will be transferred through multiple conduits from the source to the sink. So from the words, you will figure out that this is the source that we'll be using. It's a heat flow rate source. If you can look up the problem definition, you'll see that I have specified the source as a electric heater coil, which provides thermal energy or converts electrical energy to thermal energy at a specified rate. And you can use this kind of block, a heat fluorescent source block, in order to specify such sources. And our conduits would be transfer of heat from the sphere to the atmosphere through convection and through radiation, and we'll be gaining some, the orb would be gaining some heat due to radiation absorption from the atmosphere as well, right? But so far you only see two conduits, and though in fact in the diagram that we drew we had three. See, we had three conduits, but in the simscape diagram we only have two. Well, for the reason, the reason for that is the radiation heat transfer blocks deals with both emission and absorption. So it doesn't deal with only absorption or emission. It deals with both emission and absorption. That's why by simply specifying the area uh, and something called the radiation coefficient, which is actually the multiplication of the Stefan Boltzmann constant and the emissivity, you can use that to model both emission and absorption. The issue being that you will be kind of limited to, you won't be able to specify one coefficient for absorption and another for emission, which is what you would see in real life. This is kind of an issue over here, but however, we'll have to deal with it. This is another limitation that you have to keep in mind when you be using these tools for advanced thermal systems modeling. Right? But for our case, it's fine, since according to my assumption, the emissivity of orb is 1 for all frequencies, and it's invariant of frequency, therefore the same. So we'll be using 1 for both emission and absorption, and therefore it would suffice for our case. And we have heat transfer to convection block, and we had to specify the coefficient. And as you can remember, we found 25 from the chart that we looked up. Now we describe the conduits, the source, and we'll have an accumulator and a sink. So even though I call this a sink, I have used the temperature source block. Since Cape does not have blocks called sinks, it only has source blocks. However, we'll have to use the source blocks to implement sinks as well. So a temperature source block would act like an ideal energy source which would maintain a constant temperature. And so maintaining that constant absolute temperature at a certain point is what it does. If it's used as an source, it would provide energy, and if it's used as sink, it will absorb energy. Right. So this is kind of a passive source block. This what I have highlighted is its objective, that is to maintain a temperature, and based on how it's connected, based on how we have arranged uh, our network, will uh, determine whether it's actually acts as providing energy or sinking energy. Right. Okay, now the only thing that we have to left is our discuss is left to discuss is our accumulator, and for that we use a thermal mass block. So you can see it only has one port. That means it's not something that will connect in series. You know, it's not something that you connect in a manner which so that energy flows through it, but instead it so while energy is flowing throughout these lines, it can either go into the thermal mass or at the same time it can retrieve energy from that and move on. So what we specify is the mass and specific heat which we found from the data sheets or using Google Map form, whichever we prefer. So that's that. That's it for our thermal systems model diagram. We have the composite block solver configuration. I really didn't change anything over here. I just left it at default solver of variable step auto, and it will figure out what's best based on what we have specified over here at the time of compilation. We see another set of blocks over here which are sensors, which just sense how much heat is being transferred through, pay attention to the search through each of these conduits. And I have another sensor. Is not a through sensor but an across sensor. As you can see, I have connected one node to the thermal reference and the other node right after the heat source. So this is where port A is connected to, and that is directly connected to thermal mass. So what this temperature sensor would output is the temperature of the thermal mass. If you need more info about how to connect thermal temperature sensors and which direction is the positive, you just need to double click on it and bring up the help. Right, so that's it. The last remaining thing is that unlike in previous cases, we'd have to run the simulation for quite some time in order to actually visualize the dynamics, expected dynamics of the system. So I am running it for 2.5 hours. And if you can remember, I told you this in lecture 5 or 6 that stop time or simulation runtime is something you have to figure out by yourself based on what you want or to see or what you expect to see and the physical characteristics of the system. So if my system had an extremely larger thermal mass, perhaps I would have needed a longer simulation runtime. And had the thermal mass been smaller, I would have required a lesser simulation runtime. That depends. And uh, prior to moving on to Simscape implementations, developing a mathematical model, solving simple mathematical models, solving these, and being kind of aware or familiar with what you might expect is quite handy when determining the stop time. Still, it won't give you a hard and fast set of rules on how to figure out the stop time. But before moving on to Simscape, you had solved a lot of such equations and seen the solutions of these equations like this, then you would know what to expect. You would know what kind of plots to expect. And if you set some such time and run it and don't see that kind of uh, plot behavior that you would have expected to see, then you would have to change the stop. But without that knowledge of what to expect, then you don't know what stop time you need to run it for. And this is what I observed with the questions that I got from you prior to the submission. You had issues with figuring out what the stop time is. Based on the previous exercises that we did in other domains, you ran it. Most of you had run it for a small time and had gotten quite simple graphs without any meaning. So it's uh, so that knowledge is quite something you'll gain with solving with time spent in modeling and solving systems. Even after this module, I'm not going to say that you'll have all the info and all the experience that it needs to that you need in order to determine the stop time at once. Still, uh, you still have a long ways to go before you are extremely competent at that. So just like in any other software or any other skill, this is once again this electronic system modeling area is once again packed with such cases where you need some experience or some time spent on modeling things uh, prior to getting all the simulation parameters first at the correct at the first shot. Right, so now I have run the simulation and just let me open up the heat flow rates. I did click on. So we'll have to wait a bit until it opens. So now going back to here we are with the plots that I expected. The heat supply is constant throughout. Convection losses and the radiation losses experience some rapid growth, and then the growth lowers, and finally they also settle to a certain value. So based on what I see for the heat transfer rates, after 3000 seconds, I think perhaps the temperature would have settled to some point as well. So they are a bit as yes, after 3000, oh no, let's say after 4,000 seconds, things would have settled and the temperature would settle at 358 Celsius. So that's the equilibrium temperature of the system. And models such as this would enable you to figure out what the equilibrium temperature would be. Right? So in a real world, if you were to design an iron, a cloth pressing iron, then this would be kind of what you have to model. But since it's a whole system again, perhaps you can elaborate on the heat flow rate source and include the electrical system over here as well. Okay, so that will conclude our model. And the take home skills from is that when writing those equations, either when it's writing those equations, or either when you are specifying the properties of the Simscape blocks, you need to be aware of selecting the proper heat transfer coefficients and proper cross-sectional areas and exposed areas in appropriate manner. Any other areas that you need to pay attention to are quite mitigated, since we mitigate a lot of errors and when it comes to Simscape, and these blocks handle the equations behind the curtains. So most of the rules of errors will be eliminated due to us using Simscape. However, these key skills cannot be avoided. Right. So you all had completed the assignment and submitted them on time as well. Okay, so we can conclude the lecture. Uh, Best of luck for your exams.